All right, well, number 5 was definitely the more complicated, or the hardest problem here, at least on the sample test. So I think if you're doing okay through number 5, you should be in pretty good shape going into the test. But we have a little bit more coming up here. So number 6, at 100 degrees C, equilibrium constant for this reaction given is 2.19 times 10 to the minus 10th. Then we're given concentrations of all of the components, okay? And asked, is the system at equilibrium? If not, in which direction will it shift? So this is Q again. We've got a system. We don't know if it's at equilibrium. If it's not at equilibrium, which way is it going to go? Right? So the idea here is to solve for Q and then compare that to K. Now, these, I think, are, at least in my mind, these are pretty straightforward problems. The issue here is making sure you realize what problem you're working on. Right? This is not as complex as what we saw here in number 5 or even in number 4. But if you don't recognize this as a Q problem and you start trying to do an ice chart and trying to figure out what to call X, that's where you're going to run into difficulty with this particular problem. Once we're given all the concentrations, there's no X. But there is this distinction between a reaction that isn't at equilibrium versus a reaction that is at equilibrium, and that's really what we're looking at here. So for our reaction, let me just recopy the reaction here to think about the equilibrium constant expression, Cl2. Okay, all gases, which is important there up there, but I didn't rewrite the gases, but that means that Q, since we already know this, with this set of components we have may not be at equilibrium, let's just write it as a Q. Products, be carbon monoxide times chlorine over reactants, which is the kind of combination of those two pieces together in one molecule. Right? And that's it. There are no exponents there. There are no non-1 stoichiometries in the equation. Remember, those would show up in an equilibrium constant if they were present. So if we plug in all our concentrations, we can solve for Q. And again, comparing that to K will give us the ability to determine which way this is going to shift. So the carbon monoxide concentration is 3.3 times 10 to the minus 6th. The chlorine concentration is 6.62 times 10 to the minus 6th. And the concentration of the reactant that would go on the bottom here is 2.00 times 10 to the minus 3rd. No exponents, so all we have to do is plug that in. That'll give us the value we're looking for. So 3.3 to the minus 6th times 6.62 times 10 to the minus 6th divided by 2 to the minus 3rd. You do have to punch in all your exponents correctly here, though. Now, I'm really kind of limited to 2 significant figures. Not really an issue with the Q problem because it's the comparison that we're interested in, not the actual value. But this comes out to be 1.1 times 10 to the minus 8th, right? And that's the value of Q. Now again, we're comparing that to K. So K, we were given is 2.19 times 10 to the minus 10th, right? Now, 10 to the minus 8th, that's a bigger number than 10 to the minus 10th. So Q is greater than K here. And again, if we think back to this equilibrium constant expression, if Q is a larger number, that means too high up here on top of the fraction and or too low here on the bottom of the fraction. If we can bring the number on the bottom of the fraction up, that will lead to a smaller value over here, right? We're basically dividing by a bigger number. Now that happens in conjunction with bringing the concentrations on the top down or to a lower number. So by doing that, increasing the concentration of the reactant and lowering the concentration of the products, we would bring down the value of Q, right? And that would happen until we got to the equilibrium constant. So if Q is greater than K, that means this equilibrium is going to shift to the reactant side. We're going to form more of the reactant, and we're going to have less of the products. And in fact, that was the same as the Q problem we saw right at the beginning of the test. So the other option or possibility would be that Q is less than K, if that's the case, we need to bring up the value of the expression. We'd want more of what's on top of the fraction, less on what's on the bottom to make the value higher. The only other possibility here, which would kind of be a sneaky question, would be that this system is already at equilibrium. If you do Q and calculate it and it comes out to be exactly K, then that tells you this system is at equilibrium already, which means it's not going to shift. It's going to just stay there at equilibrium. Okay, I think that's the end. So just 6 problems there. These equilibrium problems can get a little longer, so maybe we'll have a couple fewer questions on this exam than you might be used to. Now, let me also point out, because sometimes people think the exam will only be the exact questions that were on this practice exam. There are several things that you should be familiar with that kind of came up here that may show up on the regular test as questions. You should know all your strong acids and strong bases and be able to pick them out. If I give you a set of bases, you should be able to tell me which ones are strong, which ones are weak, which ones aren't bases. Same thing with acids. You should be able to write equilibrium constant expressions for reactions, right? Those were all parts of some of the problems we saw here. That doesn't mean they can't be their own question when something pops up on the regular test. Okay? And we didn't do a problem here where you solved for concentrations by filling in the ice chart, where like I give a concentration at equilibrium and you can use that information to complete the changes in the ice chart. That's something you should be able to do as well. I know there are several examples of that in the videos and in some of the other review documents, but right, I can't put every possible problem on a practice test and not have it end up being as long as like one of the reviews. So make sure you're thinking about all the possible problems. Now, we can fit in, there's a bonus question here that relates to reaction mechanisms. So let me get this in before I end the video. So we have this reaction, AB plus C is then yielding A and BC as the product. And what we're told is it's second order in AB and it's 0th order in C. Right? And we want to know, what does that tell us about the mechanism and which steps are fast and slow? Now, the best place to start here is 0th order. If something is 0th order, that means the rate is not dependent on its concentration. That means it doesn't come into the reaction mechanism until after the slow step. Because remember, the rate law will only incorporate steps that occur up to and including the slow step. So C doesn't come in until the second step. So if we call this a 2-step reaction, C is not involved until step 2. Now, AB is second order dependent. That means we've got 2 different places where AB is involved in a collision in the slow step or before the slow step. So the most likely thing here is that 2 molecules of AB collide. That would give us the second order dependence, and they form some type of reactive intermediate. Now, we don't necessarily know what that looks like, right? If we had actual atoms, we could draw Lewis structures and figure out how that might happen. But say it's something like this, where 2 ABs come together and make something like that. It's not in our overall reaction. It's not one of the products, right? An intermediate is made in one step of a mechanism and then consumed in a subsequent step. So maybe A, B, B, A reacts with C here in the second step. That produces 2 of our products. The C maybe comes in and attacks and bonds to B to make BC, and that eliminates 1A. Now, the other half of the reactive intermediate might be reproduced, which means AB hasn't changed. So that second equivalent of AB doesn't show up in our overall reaction because even though it goes away at one point, it's reproduced toward the end. But that means AB plus C yields BC plus A is our overall reaction. And since we know C was 0th order, this step must be fast. Step 2's got to be fast. And that means step 1 here, where the 2 ABs come together and make the intermediate, would have to be slow. Now, if we drew reaction energy diagram there, right? A slow step means there's a big hill that our reactions have to go up. We don't know if this is endothermic or exothermic, so we don't really know where to put the reactants and the products relative to each other in terms of their overall energy. So I'll just put them about the same. The first step would have to be a big hill, and then the second step would be a much smaller hill that once we go over the first hill, we're not going to stop before going over the second hill. So putting A, B together, that second step in the reaction is super fast, leading down to the products of the reaction. Okay, again, right there at the end is the information that I'll give you for this test. No, I don't think there's any value to trying to memorize those equations for the integrated rate laws, since they really are the result of doing some calculus on those equations. So again, I'll provide you with those formulas, but that wraps up the sample test. So we'll stop there.